Every movable object possesses certain measurable traits, such as its initial position, its initial velocity, its rate of acceleration, and its start time. Similarly, there are measurable traits when the activity has ended, such as its final position, its final velocity, its acceleration, and its finish time. Kinematics is a branch of physics that studies these properties with objects in motion. There are 5 equations that exist to predict these measurable traits, and I could just give you the 5 and that will be it for the day. But I'd rather give these 5 lessons more justice than that. Today, we'll focus on the 3 equations on the left, and tomorrow we'll cover the next 2. The 5 equations are based upon 2 measurable properties of a velocity time graph. The area underneath the VT graph represents the displacement of the object. Meanwhile, the slope of the VT graph tells you the object's rate of acceleration. Since hundreds of equations can exist for many different scenarios, let's create generic equations to cover most situations. An activity might start at an initial time and finish at a specific final time. We'll just call this delta t, or total time of activity. Even though initial velocity can start at 0, we'll give it a non-zero variable of vi, and at some point the activity will end with a final velocity vf. We also notice that there are 2 different regions for surface area. We'll label the rectangle A1 and label the triangle A2. First, let's calculate the total area underneath the curve. The total displacement can be determined by adding the area of the rectangle with the area of the triangle. The area of the rectangle is vi times delta t, and the area of the triangle is 1/2 its change in height, or vf minus vi, times delta t. We can expand the binomial on the right and end up with vi delta t plus 1/2 vf delta t minus 1/2 vi delta t. A whole vit minus a half vit gives us a half vi delta t. We can keep the formula like this, but just to clean it up a bit more, we'll factor out the 1/2 and factor out the delta t. And that's it. There's the first kinematics equation. Some textbooks write it out this way. And if you're wondering why delta t is placed at the back of the term, it's because delta t is the dependent variable, just like the variable x in math class. Vi and vf, on the other hand, are assumed to be known constants for this equation. To create the second kinematics equation, we need to find the slope of this VT graph. Here's the slope equation. However, the m in the slope equation is replaced with the letter a. Delta y is replaced with vf minus vi, and delta x is replaced with delta t. The formula is correct as is, but physics textbooks like to rearrange this formula a little bit. First, both sides are multiplied by delta t. The negative vi is then brought over to the left, and after a quick swap-a-rooney, you get the standard equation, number 2. So far, we know that the area underneath the VT graph tells us the displacement, and the slope tells us its acceleration. It seems like we've exhausted all of our ideas. How do we create another equation out of this? Well, when in doubt, sub one equation into the next one, and hope for the best. We replace the vf in the first equation with vi plus a delta t. Vi plus vi equals 2vi. Now let's expand the equation, and that's pretty much it. Equation number 3. In general, each kinematic equation only has 4 variables, and you might notice that each equation is missing one value of motion. So if each equation has 4 variables, you'll need a minimum of 3 givens to find the 4th missing variable. And that's how you generally figure out which equation to use in a problem. And again, to simplify today's introductory lesson, you don't need to worry about equations 4 and 5 for tonight's homework. Let's go through some examples together. Find the final speed if vi is 5 meters per second, a is 10 meters per second squared, and the acceleration lasts for 4 seconds. We start with our givens. We know vi, a, and delta t. We're looking for final speed, so vf. Taking a peek at our cheat sheet, which formula will help us out here? Good, equation number 2. We always write down the formula to show the reader which formula is used to solve the problem. We then sub the values in, follow the rules of bed mass, and 5 plus 40 equals 45. And the units are probably in meters per second. Now on a test, you won't have time to prove that the units are correct, but we'll prove it together right now, for kicks. Even the units need to follow the rules of bed mass, so we're multiplying meters per second squared with s, and that will get us meters per second. And meters per second plus meters per second still equals meters per second. Well, look at that. Units do work out all the time. Funny enough, scientists are so adamant about this that they'll even invent fictitious units, or unitless units, like neepers, just to ensure that units will work out. See, learning about units is fun. How about I give you a moment to try out the second part of the equation, find the total distance of travel. Pause the video, and when you're ready, we'll take it up together. As usual, always state your givens. It's a form of communication to your reader. Equation 3 looks like the equation that'll do the trick. And after you sub in the values, it's totally up to you how much work you want to show before getting to the final answer. If right after the substitution, you get to the correct final answer, you will receive full marks for the problem. However, if you made a mistake along the way, it's much harder for a teacher to give you part marks if you have nothing to show. So the minimum amount of information that you need to show for full marks are your givens, require, formula, first substitution, and final answer. And you'll need to include units at each step of the way. Remember on the first day's lesson where I mentioned about engineering disasters because units weren't communicated? That's why I stress so much importance in including units in your solution. Here's one last example. Determine the rate of acceleration required if you want to qualify as a 10-second car in the movie franchise Fast and the Furious. Pause the video and see if you can get to the final answer of 8.05 meters per second squared. This full solution requires you to rearrange your formula first. We'll take equation number 3, and the first thing that we'll do is collect like terms. So we'll isolate the terms with the letter A. And since A is connected to 1/2, we need to multiply both sides by 2 to get rid of the 1/2. A is still connected with delta t squared, so we'll have to divide both sides by delta t squared. Now we have A all by itself, and we can substitute in all our givens. Follow the rules of bed mass, and conclude with 8.05 meters per second squared. In our givens, 10.0 seconds is 3 significant figures, so our final answer is also 3 significant figures. If you're wondering, 0 is infinitely precise and infinitely certain. Tonight's homework is Course Pack 16, just questions 1 through 8. You are more than welcome to try out 9 through 14 if you're up for the challenge. You can stop the video now and get started on your homework. If you're stuck on a question, you can come back to this video, as the remainder of this video is an unscripted version of me explaining the answers to the homework.
Now if you want to speed up the video by a bit, feel free to hit the shift button and greater than sign. And if you want to slow down the video by a bit, then hit the shift button followed by the less than sign. Alternatively, you can click on the cogwheel on the bottom right hand side and adjust the play speed as necessary.
Alright, for this question we'll need the second kinematic equation, which is delta D is equal to 1/2 Vi plus Vf delta t. Sub everything in, so 1/2 times 15 meters per second forwards plus 10 meters per second forwards times a time of 8.0 seconds. Again, we follow the rules of bed mass, so we do everything inside the brackets first. So 15 plus 10 gives us 25 meters per second forwards, multiplied by 8.0 seconds. 25 times 8, well, 8 quarters gives us $2, so 200 divided by 2 gives us 100 meters forwards. However, when you take a look at your givens, they're all 2 sig fig, so your final answer should also be 2 sig fig, and the best way to represent that is in scientific notation.
So it's 1.0 times 10 to the 2 meters. And that's our first answer. All right, so in this question over here, for one thing, it comes to a stop, so we know that VF goes to 0 meters per second. Next, we take a look at the units, and the units are inconsistent. We'll need to convert kilometers per hour into meters per second. So we'll start off with 39897 kilometers per hour times, for every 1 kilometer, there are 1,000 meters. Also, for every 1 hour, there are 60 minutes. And for every 1 minute, there are 60 seconds. When we crunch through all of this, we end up with 11082.5. And what are the units? Well, kilometers divides out with kilometers, hours divides out with hours, minutes divides out with minutes, so all we're left with is meters on top and seconds below. As I mentioned, units always have to work out. Now there is a shortcut, and we'll talk more about that in the next episode. But tonight I'm expecting you to do it the long way. Alright, so that's how we got this value over here, and you can see that I carried an extra significant digit. If you recall from course pack page 3, in any intermediate calculation, so in other words, if you're not done with your homework yet, carry an extra digit before you get to the end. Okay, so now that we have our VI, VF, delta D, and we're looking for delta T, that will be the second kinematic equation again. So delta D is equal to 1/2 VI plus VF delta T. And as for the arrows on top, we don't really need it because everything here is scalar, so we can go off and erase the arrows. And since we're looking for delta T, we need to get rid of everything in front of the delta T. We'll start off with a 1/2. We'll multiply everything by 2, because 2 times a half gives you a whole. So 2 delta D is equal to, in brackets, VI plus VF delta T. And to get rid of everything inside the brackets over here, we need to divide everything on both sides by VI plus VF. So these two will divide each other out, and with a quick swap Rooney, we get delta T is equal to 2 delta D all over VI plus VF. Crunch everything in, so 2 times 3 times 10 to the 6 meters divided by 11082.5 meters per second plus 0 meters per second. And if we're careful enough, we'll get to an answer of, I'm not sure yet, because I need a calculator. So after we sub everything in, we get to an answer of 541.4 seconds. But if you take a look at your givens, your worst case scenario is just 2 sig fig. So your final answer should also be 2 sig fig. So 541.4 will reduce down to 5.4 times 10 to the 2 seconds. And that is our final answer. Alright, for question number 3, it looks like we need the second kinematic equation again, but we'll be isolating slightly differently this time around. This time we're looking for VI. So since that's inside the brackets, we got to get rid of everything outside the brackets first. We'll start off with multiplying both sides by 2. So 2 delta D is equal to the 1/2 times 2 gives you a whole. So whole VI plus VF delta T. Again, the delta T on the outside has to be gotten rid of first. So again, the delta T on the outside needs to be gotten rid of first, and I dropped my pen. So we need to divide both sides by the delta T. Delta T downstairs divides out with delta T upstairs to give you a whole. So VI plus VF is equal to 2 delta D divided by delta T. And when we bring the VF over, it'll become negative VF. So we have VI is equal to 2 delta D over delta T minus VF. Crunch all the numbers in. Sub everything in, and you get to 27.857 meters per second. Seeing that all the givens are all 3 sig fig, your final answer should also be 3 sig fig, so 27.9 meters per second. Alright, so all the objects are falling, so everything is a vector going downwards. Now we can either include the downwards in all of our calculations, or we can make our lives easier by making an assumption. So we'll just assume that down is positive. That way we don't need to worry about the d's anymore. And if we still happen to get a negative answer, then we know that we're going upwards. But it's impossible to get negative time, so if we get a negative answer, we know we did something wrong. Anyways, let's just continue from what we know here. This looks like we need the second kinematic equation, or the first, one of the two, the one that looks like this. After a while, you just memorize them, and you don't need to call them 1, 2, 3, 4, 5. We're isolating for the delta t at the end. And remember, whenever you're trying to isolate, you first collect like terms, or just do the opposite of mass, so remove any additions and subtractions. So that's why the vi goes over, and it becomes negative vi. So vf minus vi is equal to a delta t. We then need to divide both sides by a. So our delta t is equal to vf minus vi all over a. Crunch all the numbers in. So 19.4 meters per second minus 4.5 meters per second divided by 9.8 meters per second squared. And a bigger number subtract a small number still gives you a positive answer. So we know we're going the right direction. Pull up my calculator again. And you get 1.520 seconds. Seeing that your worst case for your givens is 2 sig fig, your final answer should also be 2 sig fig. So your final answer is 1.5 seconds. And we're done. Question number 5. Again, we see that there's this whole west and east business. You could sub all those values in with west and east, but it does get messy. Instead, it's much easier just to state your assumptions. So we'll just assume that east is positive. And if we get a negative answer, then we know that our final answer is to the west. Alright, so this question looks like we need this formula. Vf is equal to Vi plus a delta t. And is it a direct substitution? Yeah, after we solve for this east thing. So if east is positive, then we know that in our givens, our Vi is equal to negative 15 meters per second. Our A is equal to positive 7.0 meters per second squared. And our delta t is still 4 seconds positive. Alright, sub everything in now. So negative 15 meters per second plus 7 meters per second squared times 4.0 seconds. 4 times 7 is equal to 28. And meters per second squared times seconds gives you meters per second. And meters per second plus meters per second still gives you meters per second. Turns out that it was positive, so we know that their answer is 13 meters per second towards the east. And there's our final answer. For question number 6, it starts off from rest, so we know that our Vi is equal to 0 meters per second. And we're trying to find two things, acceleration and the final velocity. So we take our third kinematic equation, delta d is equal to Vi delta t plus 1/2 a delta t squared. And again, this formula does have arrows on top, but if we want to save ourselves the effort, we'll just make an assumption. So we'll just assume that up is positive, then we can just drop all the arrows and make our life quite a bit easier. As we're isolating for a, again, we got to first get rid of all the other terms that do not have a beside it. Alright, so when we bring over Vi delta t over, that becomes negative. So we have we have delta d minus Vi delta t is equal to 1/2 a delta t squared. We then multiply both sides by 2. So the 2 and the 1/2 divide each other out. And to isolate for a, we divide both sides by delta t squared. So we know that acceleration is equal to 2 times 4.50 times 10 to the 2 meters minus 0 meters per second times 4 seconds, all divided by 4 seconds. Quite careful now. All squared. Maybe that's where the answer went downhill. Okay, we then pull out our trusty calculator. 2 times open bracket 450 minus 0 divided by 16 gives us 56.25 meters per second squared. And if this is the final answer, then our final answer should be just 2 sig fig, so 56 meters per second squared, and we're done. Up. As we assumed up is positive. Square brackets. And if we're done, that's good. One thing I recommend that you don't do is recycle. There is a part 2, and I know it's very tempting to try to use that to solve for your VF. All right. Now, if you use 56 as your original value, you're going to have some heavy rounding error. And if you use 56.25, you'll get to the correct answer if you do everything carefully. But often we end up making a mistake, and maybe these two are not even the correct answer. So you're better off just erasing everything and starting all over. That way you minimize your chances of being further off from the correct answer. So yet again, we'll just assume that up is positive. And when we are looking for VF given the rest, that means we need to have this kinematic equation, delta D is equal to 1/2 VI plus VF delta T. Isolating for VF. I think I did this earlier, so how about I just jump right ahead. 2 delta D over delta T is equal to VI plus VF, so the VF is equal to 2 delta D over delta T minus VI. After enough practice, you can do most of the rearranging in your head. So we sub in the values, 2 times 450 meters divided by 4.0 seconds minus a VI of 0 meters per second. So after you go through this, you get an answer of 225 meters per second. Seeing that your givens, the worst case scenario is 2 sig fig, your final answer should also be 2 sig fig. So 2.2 times 10 to the 2 meters per second as a vector up. And that's your final answer. This is that weird even given at 2.25. If you're forced whether to round up or down, you always round to the nearest even. And that's why it works out to 2.2. Question number 7. There's 2 parts to this problem. Often it's actually easier to solve this problem by drawing a position time graph. So we know that at 3.5 seconds, the person is accelerated from 0 meters per second to some final value at an acceleration of 2.8 meters per second squared. After that, the runner runs at a constant velocity from there and beyond. So at some point we got to figure out what our VF is here, because that will be the constant velocity for the second half of the journey. The first question is asking how far he's traveled to this point, and that will be position 1. And we know that at position 2, that equals 100 meters, because it's a 100-meter track. In fact, that's what we need to figure out the second part of the story. How long does it take to finish the story? Or how long does it take to finish the journey? Okay. First figure out what our D1 is. So D1 is equal to VI delta T plus 1/2 A delta T squared. Since the runner started from rest, we can drop that term altogether and save ourselves some penmanship. And yeah, all you have to do is just simply draw an arrow and write the number 0. And all scientists will know that that means this term goes to 0, and it's irrelevant for the rest of our problem. So we'll multiply this by 3.5 seconds, and the squared goes over here. And that will work out to 17.15 meters. Taking a look at their values over here, if that's 2 sig fig, then if we're done here, then our final answer is also 2 sig fig, so 17 meters. Now in these problems over here, unfortunately we have to recycle this number here, and that's why I didn't want to delete it altogether. We will see it again very soon. Next, we've got to figure out what our VF is over here. So our VF is equal to VI plus A delta T. This VI yet again goes to 0, so we're left with 2.8 meters per second squared times 3.5 seconds. that will work out to 9.8 meters per second. And remember, this 9.8 meters per second is the constant velocity for this segment of the journey. Okay, so we know its speed, and we can probably determine its distance by subtracting these two values over here. Right? Well, displacement 1 plus displacement number 2 will equal a total of 100 meters. So if we need to figure out what our displacement is during this segment over here, then delta D2 is equal to 100 meters minus that 17.15 that we just went through earlier. Or more formally, D2 is equal to 100 meters minus D1. There you go. And that difference will work out to 82.85 meters. Okay, so we got our 82.85 and we got our 9.8. We know that delta D is equal to VI delta T plus 1/2 A delta T squared. However, at the segment over here, we notice that there's no acceleration, so this term goes to 0. So delta D is equal to just V delta T. So T is equal to delta D, the second segment, divided by that velocity that we had earlier. So that's 82.85 meters minus 9.8 meters per second, and that will work out to 8.454 seconds. Now the summation of all our time is equal to delta T1 plus delta T2, sorry I ran out of space here, that equals 3.5 seconds plus 8.454 seconds, and that will work out to a grand total after seeing our givens as 2 sig fig, that will work out to just 12 seconds. And that's our final answer in a nutshell. This last segment, we have car A and we have car B. They're going for a race, and that race lasts a total distance. It lasts for a total distance of 100 meters till your end. So in our givens, we have our delta D for car A, and we have our delta D for car B, and they're both equal to 1,000 meters. Car A has a constant velocity of 20 meters per second. As for car B, it starts off from rest, but it has an acceleration of 0.333 meters per second squared. Let's just clear this up because we need some space. And for the first one, we could start off with the full formula, but just like the previous question, if you notice that there's a term that goes to 0, well, I just stated over there, the formula is a lot cleaner. Delta D is equal to VI delta T. So the time for car A is equal to the distance divided by its velocity. So 1,000 meters divided by 20 meters per second gives you 50 seconds. As for car B, we have the same formula again. Delta D is equal to VI delta T plus 1/2 A delta T squared. Our VI goes to 0. So our cleaned up formula is just delta D is equal to 1/2 A delta T squared. We multiply both sides by 2, so we get 2 delta D, divide both sides by A, and that gives us delta T squared is equal to this. In other words, delta T is equal to the square root of 2 delta D over A. We sub our values in, so 2 times 1,000 meters divided by 0.333 meters per second squared, and that works out to 498 seconds. So comparing between these two values over here, we see that TA is less than TB. So since TA is less than TB, therefore, which is the triangle the other way around, car A wins. By how much? Well, let's find the difference between the two. Delta TB minus delta TA is equal to 77.498 minus 50, which gives us 27.498 seconds. The givens, worst case, is 2 sig figs, so 27. So car A leads by plus 27 seconds. And that's it for question number 8.